three main reasons. The first reason is there are lots of Nobel laureates in this image. I mean, there is John Kendrew, there is Maurice Wilkins, Max Perutz, Jim Watson, Francis Crick, Lawrence Bragg. This is Robert Corey, this is Pauling's assistant. So lots of Nobel laureates for such a small group of people. The second reason, there is only one woman, Beatrice Magdoff from the Brooklyn Polytechnic. Now, of course, things have changed. You go to a Proteins meeting today, easily 50% are women. So things have changed. I should also, I mean, this talk is about Pauling, but of course I want to always emphasize Rosalind Franklin's contribution to the Watson and Crick model. I mean, without seeing her X-ray diffraction image, Watson and Crick probably could never have come up with their model. And conversely, had actually Pauling seen her X-ray diffraction image, he probably would have known it's a double helix and not a triple helix. And the third reason is a simple one. I mean, this was a science meeting. It was not a business meeting, a science meeting. Look at them. They're all wearing ties, for heaven's sake. I mean, even I'm not wearing a tie now, and hardly anybody here wears a tie. But at science meetings, they were all wearing ties. So things have changed. My last person is Albert Einstein. This is the photo of Einstein that I like best. Partly because when my hair is a little bit longer, it looks just like that. And that's, by the way, not where the similarity ends. You see, I like to say that Newton is dead, Einstein is dead, and I also don't feel so good. Now, Einstein, of course, is best known for his theory of general relativity. This is already 2 years before he published this theory, when he tries to explain to astronomer Hale how the sun is going to bend light in his theory. But of course the main thing is that he eventually wrote this famous equation, which I was once asked by a reporter. They were trying to make a list of the 10 most beautiful equations that exist, and I nominated this one, and it's still there on the web, is my nomination for the most beautiful equation. Now, some of you may be a bit rusty on your general relativity, so I'm going to only explain to you the principle here. So for a moment, forget about this term for a moment. But what does these things do here? So this thing here describes the geometry of space-time. So it's a bit like, you know, you have a trampoline. It can bend in various ways. That's the geometry. So it has a certain geometry. This thing here describes the mass and energy content in your volume or in your universe, if you like. And this is the strength of gravity. So what does this equation say? It says that mass and energy cause space-time to bend somehow. So it's like me standing on a trampoline, I cause it to sag. And the force of gravity that comes out of this is just an expression of the curvature of the space that is formed. So a little bit like, you know, again, to continue with the trampoline, I stand on the trampoline, I cause it to warp, and then if I throw small balls onto that, they will try to find the shortest path in that warped space. So the sun warps space in its vicinity, and the planets find the shortest path in that warped space. So gravity is not some mysterious force that acts across distance. It is just an expression of this curvature of space. That is the essence of this equation. Now, as soon as Einstein wrote this equation, well, not immediately. He published this in 1915, so we celebrated last year 100 years to general relativity. In 1917, he tried to apply this equation to the universe as a whole. But when he tried to apply it to the universe as a whole, he discovered that there is a problem. And that's the following. Okay. In Einstein, in 1917, they didn't know about the existence of other galaxies other than the Milky Way. So he was talking in terms of stars. But he thought that all the stars should be fixed in their places, that the universe is static, because he thought that that is a more elegant type universe, you know, where everything is static. But, he reasoned, how can the universe be static if every little piece attracts every other little piece? Then this thing should just collapse under its own weight, basically. It cannot stay static. So what he did, he came up with this clever idea to add this term, which has in it this thing which we call the cosmological constant, which at every point in space, if you found that from gravity there was a force going this way, what that term did, it did a force exactly equal in the opposite direction, so that things would stay in equilibrium. Okay? This was a clever thing, you know, that in every point it balanced everything. Now, it was clever but not fantastic, because even though, it turns out, even though he created an equilibrium this way, it was actually an unstable equilibrium. I mean, you know, like, I can try to balance this thing on my finger and I may even succeed, but the slightest perturbation will cause it to fall, right? So it was not in that sense, but at the time he didn't know about that, and he thought that he had this wonderful solution, which was, you know, everything in equilibrium. However, in the late 1920s, these two gentlemen, this is the priest and cosmologist Georges Lemaitre from Belgium, and this is Edwin Hubble, after whom the Hubble Space Telescope is named, discovered, and there is a whole story about that, which I describe in the book, but it's a very, very fascinating story, but they discovered that our universe is not static, it is expanding. As soon as Einstein heard that the universe is expanding, he said, wait a second, if the universe is expanding, I don't need things to be in equilibrium, because all that gravity will do, it will slow down the expansion. In the same way that, you know, I throw something up here on Earth, it's not in equilibrium, only the gravity of the Earth acts upon it, but what it does, if I gave it some speed, the gravity of the Earth simply slows it down. So the universe is expanding, gravity will slow it down. That's what he said. So, in that case, he said, I don't need that extra term. And he took it out of the equation. Okay? Now, again, you will hear entire books have been written claiming that Einstein called that his biggest blunder. Again, I did a lot of research on this. I'm afraid you'll have to read the book to find out what I discovered. But in any case, he took it out. He certainly regretted having put it in, okay, because it wasn't needed. Well, in 1998, two groups of astronomers discovered independently that the expansion of our universe is not slowing down. It's speeding up. It's speeding up. It's, you know, like, imagine I throw this up again, and not only is it not slowing down, it's speeding up towards the ceiling. You know, I once gave a talk on this accelerating universe. There was a 7-year-old who sat in the front row. And I said, what would you have said if I did this? I would throw my keys up and they would accelerate toward the ceiling. And this kid went, magic. And it is like magic. You know, it's true. I mean, basically, something has to kind of push to make this acceleration. And do you know what's that thing that pushes? As far as we can tell, although we don't know for sure yet, but everything is consistent with that the thing that pushes the universal expansion to accelerate is that term that Einstein took out of his equation. I mean, you know, some people, they are so smart that when they think they made a blunder, it turns out to be some great insight. So Basically, if Einstein made a blunder at all, was not putting that term in, was taking it out. And in not taking it out, he could have predicted that the universe should be accelerated. Okay. At this point, I've actually finished what I want to say about these three people. But I want to come back to the question of why did I decide to write a book about blunders? And here is the thing. In most textbooks, news stories, in school, and even at university, we are continuously taught as if scientific progress, and in fact not even just scientific progress, but progress in almost any creative enterprise, is a direct march to the truth. Now, anybody who has ever been involved in scientific progress or in any creative work knows that nothing could be further from the truth. You know, it's not, Newton didn't sit under the apple tree and apple fell on his head and he jumped his head. Of course, F equals gm1 m2 over r squared. It didn't happen like that. Progress in science is achieved through a zigzag path with many, many false starts, many blind alleys, many places where you need to go back to the starting point. So that's one thing I wanted to convey. But I wanted to do something more than that. You see, I called my book Brilliant Blunders, not Sloppy Blunders, or something like that. What do I mean by that? There are blunders that are inexcusable. These are blunders that are made because asked him, well, tell me some magic. And the student gave him 10 different answers of how he would use the barometer to measure the hot. So the first was that he's going to drop the barometer from the roof of the building and measure how much time it takes to get to the ground. The second was that he will tie the barometer to a string, lower it from the roof, and measure the length of the string. The third was that he would hang the barometer on a string and use it as a pendulum and measure the period at the top of the building and at the bottom of the building, and from the difference in the free fall acceleration he would tell the height. The fourth was that he would take the barometer and put it against the wall of the building and measure like this. And my favorite answer was that he will go to the custodian of the building and would tell him, look, I will give you this really nice barometer if you tell me the height of the building. Now, the professor, according to the story, asked the student, what, you don't know what answer they wanted? And he says, of course I know, but there is no reason for me to give you that particular answer. That story goes on to say, and this is very appropriate for a Perimeter Institute, that the name of the student was Niels Bohr. Now, this is again one of those apocryphal stories that is almost certainly not correct, but it demonstrates what I'm talking about. Okay? So that is my point. I want our education system, everything, to adopt methods that will actually encourage brilliant blunders. So basically, I'll finish by saying that scientific blunders, and by this I mean these brilliant blunders, can actually be the portals to discovery. Thank you very much. Perfectly okay for those people to say, you know, after they look at all kinds of possibilities, we know that this
Yoda. Did not work. So then he turned to the statistical mechanics, which he did not like.